it will all be beautiful theories. So, that's what you care about. You're in for fun. And the next 2 hours will be that. Yeah, or
How much more than that? What's my? All right, thanks for having me. Yeah, so I'm going to give a broad overview of proof systems in practice. It's obviously a huge topic, like a flood of papers coming out pretty much every day. So I have to focus a little bit, and I'll naturally focus on the approaches I personally think will be most impactful in the coming years. But again, I'll try to be as broad as possible. Here's some ridiculous disclosures I'm required to show. Okay, so what is a SNARK? As we saw from this morning, this is a cryptographic protocol that lets an untrusted prover prove it knows a witness satisfying some property, right? And the S in SNARK means succinct, and that just means that the proof is short and fast to check. All right, so today for SNARKs in practice, I want you to think of the following kind of tooling pipeline. This is how someone might go and deploy a SNARK without knowing anything about how they actually work under the hood. So we're going to have the developer write a computer program in ideally a high-level language that they're comfortable writing computer programs in, Rust or C or what have you. And that program will take as input a purported witness and just check that the witness is valid and like satisfies the property the prover claims it satisfies. All right, and so the tooling then, the developer will then hit a button and say like, snarkify this program, right? So the tooling will kind of automatically turn that computer program into something like a circuit, right? Because kind of like the native language of proof machinery is like circuits and low-degree polynomials and things. Similar to how your compilers on your laptop turn high-level computer programs into machine code, circuits are like the machine code of SNARKs. Yeah, I will explain by the end of the 2 hours like how you might actually build this kind of tooling. Yeah. Yeah, so there's, the tooling has kind of two pieces. So there's the transformation from the high-level witness, computer program that checks the witness to something like a circuit. And then there's a SNARK to prove that the prover actually knows the satisfying assignment to that circuit. And right, the first step is often called the front end, and the second step is often called the back end. And the line between the two can blur a little, but I think it helps a lot to try to have that line there to the extent possible. Yeah, so now let's just dive right into the back ends, which is where all the proof machinery that we love to study works. And so designing SNARK backends typically works in a three-step process. We've actually seen all three steps in the morning, just slightly different terms, PIOP instead of PCP and what have you. But yeah, so first you design a protocol that's called a Polynomial IOP. I'll tell you shortly what that means. Next, you design a cryptographic protocol called a polynomial commitment scheme, and you can just put these two together to get a succinct interactive argument. And typically, it will be public coin, and then to get rid of the interaction, you apply fiat shamir. Great. So this is how basically all SNARKs are designed today. There are a couple exceptions, but even those exceptions are sort of barely exceptions. And so, I think it's not really a lie to just tell you this is more or less how all SNARKs are designed. And so let's stick with this design paradigm. All right, so what is a polynomial IOP? Okay, I'm actually going to tell you a special case of polynomial IOPs, which will suffice for today. So the very first message the prover sends in this protocol is a little funny. So it actually specifies a polynomial, okay? And you should think of this polynomial as pretty big, right? So if the prover is claiming to know a satisfying assignment to a circuit, this polynomial is like as big as that circuit, right? And so it could be univariate, it could be multivariate. If it's univariate, it's like, if your circuit has 1 trillion gates, the degree of this polynomial might be 1 trillion or even 2 trillion or 4 trillion or something. Okay, so the prover we think of as sending that polynomial to the verifier, but it's huge, it's like as big as the circuit. So we don't want the verifier to have to read a complete description of the polynomial, 1 trillion coefficients or something. So we're going to give the verifier limited access to the polynomial. We're only going to let it evaluate the polynomial at one point of its choosing. Okay, and so that point actually is going to be determined over the course of stage 2 of the protocol. Don't worry about that for now. So yeah, so the prover sends this polynomial. It's big, but the verifier doesn't read the whole thing. It's only going to evaluate it at one point. And then the second stage of the protocol, they just run a standard interactive proof where the verifier reads all the prover messages in full. Okay, and so the way these two stages, yeah, go ahead.
If the polynomial has a huge degree, even if you value one Why it takes 7 steps?
For the prover.
Oh, but we trust him? Sorry, but if the, what's the point of sending it if the prover that like the verified then needs to
Right. What's the point of sending it? I mean, so that's where the polynomial commitment scheme comes in. In the end, the prover will just succinctly commit to the polynomial.
so the prover will prove it to him basically.
Yes. Yes. Yeah. So in the final SNARK or succinct interactive argument, the prover will provide the requested evaluation of this H and the proof that the requested evaluation is consistent with the H it sent.
So it's not permitted to evaluate, it's permitted to get the value of it.
Yes.
the H of
Yeah.
it.
Yes, sorry. So it's query access. It gets to ask for one evaluation of the polynomial. Yeah. And the prover gives that evaluation. Yeah. Okay. So what's happening in these two steps is this polynomial H often encodes, don't worry about what that means for now, encodes a witness for the prover's claim. And then stage 2, the prover is proving that that witness is valid. Okay. And sort of the point of stage 2 is to reduce a global claim, which is saying, you know, this witness is valid, like every single entry of the witness is correct, to a local claim, meaning a claim about just a single evaluation of H. All right, and of course, we'll see some polynomial IOPs soon, and then this will be a little less abstract, okay? But at a high level, there are two classes of polynomial IOPs. One, the polynomial is univariate, okay? And the key technique in stage 2 to do the global to local reduction is something I call quotienting. And these are typically constant round protocols. So stage 2 is just a constant number of messages exchanged. And the second class uses multilinear polynomials, so that's like multivariate, and the sum check protocol. And so these have logarithmically many rounds. Okay, so high level comparison, what I'm about to say is still a little bit controversial, but I think people are coming around to the accuracy of the statement. The first approach with univariate polynomials is better for verifier costs, depending on what commitment scheme you use. And the second is better for prover costs. Okay, these two things are often in tension: faster prover, worse verifier, and vice versa. Now, even for the second class, it's not like the proofs are huge. They're still logarithmic in size. And concretely, it's kind of like every time you run the sum check protocol, you're talking about 2 kilobytes in the proof, and you might run it several times, so your proofs might go up to a dozen kilobytes or something. And you know, then even if your proof is pretty big, we can typically bash the proof size down further, and I'll mention that in a little bit. Okay, and so now moving on to the second component of a SNARK and SNARK design, a polynomial commitment scheme. What is this? I mean, it's basically exactly what we need, as Yao's question indicated, to turn the polynomial IOP into a succinct interactive argument, right? So the polynomial the prover sends in message 1 is big. We can't have the prover actually send that polynomial to the verifier, so it's just going to send a succinct commitment to it. Often this is just one hash evaluation or one, you know, cryptographic group element. And you know, the commitment is binding, right? So it's almost as if the prover sent that whole polynomial, even though it didn't, is the intuition, right? And then at the end of, you know, the interactive proof, like stage 2 of the protocol, the verifier, you know, knows what point it has to evaluate the committed polynomial at. So it says, hey, prover, tell me the evaluation I need and give me a proof that the answer you're giving me is consistent with the committed polynomial. Okay, so that's a polynomial commitment scheme. Again, you just naturally put it together with the polynomial IOP and you have your succinct interactive argument. Okay, now there were 2 classes of polynomial IOPs. There are right now like 4 classes of polynomial commitment schemes, at least that are on the verge of practicality. Okay, so the first is it uses pairing-based cryptography and a trusted setup. The most famous in this category is KZG commitments. So in green, for each of the classes, I put kind of the most well-known, the most popular scheme in the category. And in each case, at least until recently, the reason for the popularity is basically because the verifier costs are best in its category. Okay, so KZG commitments have sort of the best verifier costs around, okay, but they do need pairings and a trusted setup. All right, next category, you don't necessarily need pairings. You're still using elliptic curve groups. And no longer is there a trusted setup. Okay, and the most popular in this category is called bulletproofs, also called IPA for inner product argument. So this still has very short proofs. Unlike KZG, it's not constant size, it's logarithmic in size, a couple kilobytes. Go ahead. Transparent means there's no toxic waste. There's no structured reference string, yeah. So like,
public
okay, public, yeah. And to get a little more concrete, for like bullet proofs, the common reference string is just a bunch of random group elements. Yeah, so bullet proofs, the proofs are still really short, but the verifier is slow. Okay, there are other schemes in this category that don't have a slow verifier, but the proofs get a little bigger. Okay, and then there's hashing-based schemes. So these are transparent and plausibly post-quantum, right? Anything that uses groups is not plausibly post-quantum. The most popular one in this category is Fry. Again, until recently, that had the best verifier cost in this category. Now this has come down a little bit with Stir and also Were. And then there's this new category, which I'm quite excited about based on lattices. This is still maturing, okay? But I'm hopeful that basically this lattice commitments can mature into a drop-in replacement for at least category 2, let's say. And now you'll be post-quantum, you'll avoid some of the other downsides of elliptic curve groups. And I'll highlight some of the potential open problems here. Okay, so in general, you can take any polynomial IOP that you like and any polynomial commitment scheme that you like and blend them, put them together to get your succinct argument. The one exception to this is if your polynomial IOP uses univariate polynomials, your polynomial commitment scheme better work for univariate polynomials. Similarly, if your PIOP uses multilinear, your PCS better work for multilinear. Yeah.
When you mentioned IOPs, you said in one of them it's 2 rounds and in one of them is, do you really care about the rounds or you care about the total communication?
You care about the total communication and that fiat Shamiring the thing is secure. In general, for many round protocols, fiat Shamir might not be secure even, in the random oracle model, but, for the protocols we actually care about, they all have nice properties that means fiat Shamir is secure for them in the random oracle model, and I will talk about, the complications that we've already heard about today.
And these 2 classes, they have similar total communication complexity?
So the communication comes from 2 places. There's the polynomial IOP, and then there's also the evaluation proofs on the polynomial commitment scheme. And so the situation is the univariate stuff, if you combine it with something like KZG commitments that have really short evaluation proofs, that will give you shorter proofs than you can possibly get with something like SumCheck and multivariate. You can also combine the 2 through composition, which I will mention shortly. But anyway, so yeah, so what I would say is like kind of everything can be logarithmic proof size and verifier time from like all the classes. If you really want constant, you need univariate and KZG, and there's kind of no way around that, more or less. Yeah. Other questions? Okay. All right, so let me summarize the state of SNARK performance today in practice. So generally, the verifier is cheap. I mean, at a minimum, this means like the verifier really is like, much less work than the verifier of the trivial proof system. The trivial proof system is when the prover just sends the witness and the verifier just like runs the computer program on the witness. But there is considerable variation in verifier costs. So these things that use KZG commitments or, stuff similar to KZG commitments, they'll have proofs as little as like half a kilobyte or something. Okay, the hashing-based evaluation proofs for something like Fry, the polynomial commitment scheme, they'll be roughly like 100 kilobytes and up, and exactly how big they are depends on how aggressive you are with security, concrete security levels and assumptions and things. Yeah, but I mean, basically, your verifiers are running on the order of milliseconds, right? It's like they're fast. The proofs are like pretty short, but that doesn't mean that there isn't multiple orders of magnitude variation in how big the proofs are, depending on which category commitment scheme you use or what have you.
How much USD is the 200K gas?
Well, that'll fluctuate with Ethereum prices. I think it's not that much, dollars, like not hundreds of dollars, I think, unless, something is happening that's driving gas prices way up. I think that's the right ball. I'd have to, yeah, I'll check over the break and, give a more confident answer to that question. Yeah.
Can you explain the gas terminology?
Yeah, sure. So in blockchain applications, these proofs are getting posted to the blockchain, and every blockchain node in the world is verifying them. And so you need to charge people money to make sure that they're not, because anything that they insist be verified on chain, like literally every blockchain node in the world, hundreds of thousands of computers are all verifying those proofs.
So it's using like a Bitcoin type of rather than consensus or something.
People submit these transactions and they'll say, hey, I'm willing to pay this much, to get my transaction into the chain.
Gas is how much they're paying.
Yeah, so gas is just how Ethereum measures like how much work is being done.
But the work is computational work.
Yeah, so I mean, like the data storing the proof has some cost, and gas, and there's also computational cost, and I think gas refers to the combination of the two. Sometimes people don't post the proofs on the blockchain, and anyway, so yeah, this gas stuff is just the verifier is running, like the blockchain itself is the verifier, and
It's less than an LLM.
yeah.
Or gas or whatever you call it.
Yeah, no, I mean, again, like verifying one of these proofs on chain might just take milliseconds, but like, Ethereum will still charge you a meaningful fee to, have that millisecond computation running in every blockchain node in the world, every Ethereum node in the world. So yeah, so like one proof, not that expensive in dollar terms, but if you're posting these proofs to the blockchain, every few minutes, that'll really add up. I mean, blockchain projects literally pay millions of dollars a year to verify these proofs today. And the proofs are full of bugs, so, and they're still paying millions of dollars a year to verify them. But anyway, yeah, does that?
Hopefully you don't verify it if it's bug.
Yeah, I mean, I think what's really happening typically is only whitelisted entities can post the proofs because we don't really trust the security of the proofs. I will talk about some of this at the end. Yeah.
The whole point of this is to ask them, what's the kind of ballpark ratio that they're actually saving by going through all the trouble with doing it?
Yeah, I mean, so the verifiers are, I think, direct witness checking for a lot of these things is more than a few milliseconds, right? If you're, like these blockchain rollups, like there are like a lot of transactions that might be covered in a single proof. And so, actually verifying all those transactions directly, way more than a few milliseconds, right? So you are saving work. You could, yeah, so that's just pure verifier cost, right? Now, of course, the prover is doing a lot more work than native execution here. The costs of running the proof system are not just checking the proof, it's also getting the proof out of the prover. And if you take that into account, there are more questions, yeah. Other questions? Yeah.
Seeing here, it doesn't really matter what the size of the circuit or the width is. For any circuit, it's basically the same 200,000.
Yeah. So like Groth 16 and Planck, their proof size is constant, like independent of the size of the statement being proven. Sort of, it only depends on the security parameter in a theoretical sense, but in practice, that's just fixed to 128 or whatever. And then, something like Fry proofs, they grow like polylogarithmically, but, for any reasonable value of n, it's still going to be in this ballpark of 100 kilobytes. Yeah. So, the prover has to deal with these giant circuits, but the verifier, because it's a sickness, is like fine with giant circuits. Yeah.
300,000 gas is about 70 cents right now.
Okay, great. Ethereum has become a lot less congested in the last year or so. So my numbers are like 3 years out of date. So thanks, Benedict. So each proof is pretty cheap, but if you're posting tons and tons and tons of them, it'll still add up. All right. Okay, so SNARK verification, generally cheap. SNARK proving, generally expensive. So today, for general computation, you're talking about the prover is on the order of 1 million times, doing 1 million times more work than just running the computer program with no proof. Okay, now to be clear, this million-fold overhead is highly parallelizable, right? So you can like throw hundreds of GPUs at running the prover, in a parallel way, and kind of try to eat away at this overhead so you're not waiting forever for the proof to come out. But still, like million-fold overheads are like not okay except in very limited applications. So today, like the blockchain community is like really, really focused on proving Ethereum blocks, getting the proof out in under 12 seconds, because there's a new Ethereum block coming every 12 seconds. And you still can't really do this today with, under a couple hundred GPUs, and people are only just now getting close with a couple hundred GPUs, right? And like one Ethereum block is just really not that much computation getting proved, and yet we need a couple hundred GPUs, right? I mean, people are amazed you can do this at all, But the converse is, you need a couple hundred GPUs to prove very, very little. Okay, and on top of that, Ethereum wants to 100x the amount of work that needs to get proved in the next few years. And so now, 100 GPUs is turning to, what's that, tens of thousands of GPUs. Like our provers need to get faster, clearly, right? And if you want to use SNARKs outside of blockchains, you're going to be proving much bigger statements, probably. Yeah, so we need the provers to get faster. All right, I do think this overhead of 6 orders of magnitude is falling, and I think within a year or two it can go down to about 4 orders of magnitude. Still a lot, but now I think that's low enough that some interesting new things will be possible that aren't possible today. Okay, so I'll generally focus on prover time for the reasons I just said, right? It's the main limiting factor for SNARK applicability. But on top of that, and I've indicated I would cover this, you can kind of get the best of both worlds in a generic way, which is through SNARK composition or recursion, right? So if you have a fast prover SNARK where the proofs are kind of big, what you can do is you can declare that kind of big proof not the final proof, and then use a small proof SNARK to prove that proof. And now that's the final proof. And so you're applying the slow prover, like the small proof SNARK, only to a circuit implementing the first SNARK's verifier. So as long as that circuit is smaller than the original thing you were proving, it doesn't really affect prover time. Okay, so that's another reason to focus on prover time. As long as your SNARK is reasonably succinct, it's kind of generically enough to then go all the way down on the proof size. All right.
Is that something that people have attempted to do in practice yet?
Yeah, it's this is used all over the place.
Like specifically, like combining like a growth type proof with a.
Yeah.
Okay.
Yeah, most proofs that are going on chain today are you take a hashing based thing, you're not happy with the 100 kilobyte proof or whatever it is, and so you grow 16 or Planck prove the hashing proof. And it's still an engineering headache, right? I kind of wish we didn't have to do this.
Yeah,
and
turning one verifier into something that you can prove something about in the other proof system seems.
Yeah, it's kind of gross, and yeah, and sometimes it can actually be kind of prohibitively expensive. And I'll say more about this. One of my goals is to make people use less SNARK recursion and composition for reasons like this. Okay, so differences between the morning and the afternoon. Right, so in practice, we are way more aggressive with assumptions. In general, we tend to be fine with the random oracle model, as well as obviously standard assumptions like discrete log, which unless you're focused on post-quantum security, even the theorists are fine with, right? Often we'll go even further than random oracles, like we'll work in other idealized models like the algebraic root model, what have you. We'll happily, compose one SNARK with another SNARK, even though you will no longer have security in the random oracle model and things like that. Some practitioners even just kind of assume current attacks are exactly optimal without even something like security in the random oracle model. They'll even do this just to save like a factor 2 on proof size, which I don't think is a good trade-off, but that's the culture right now. So generally pretty aggressive with security, right? We're just, not really going to worry too much about that today, in this afternoon, yeah. So typically whenever people are deploying Fry today, they are assuming known attacks on Fry are exactly optimal, and this just saves you a factor 2 in proof size. And if you're doing recursion, that factor 2 in proof size just turns into like you're pushing that onto the prover, and so it's saving you like a little bit on prover time actually. And I think people should stop doing that.
So are people trying hard to attack it? To like.
Yeah, I mean,
Proof of security, I'm going to come up with an actual attack to show.
People are definitely thinking about that problem. And in fact, I think I expect some of the more aggressive conjectures to be disproved at some point. Now, will they be like disproved to the point where what people are doing is attackable? I doubt that.
Right, I think that was the trajectory in security, right? People did random things that were not provable, but it's fine.
Yeah.
And then people translated theoretical, things to actual attacks. You don't think it will happen here?
Provable just with more aggressive security parameter.
No, but it's not provable. The composition is not provable even in the random oracle model.
Yeah, so, okay, so, yeah, so people are doing a lot of things without theoretical justification here. I don't see SNARK recursion going away. That's not going away. I think this sort of saving a factor 2 in proof size, I hope that goes away. Okay, questions? I saw your hand first.
Yeah, I was just gonna ask, like, what are the financial consequences of the attack? Or using this?
Yeah, I mean, again, I think that these things are still full of bugs today. They really are. I expect that to get better in the next couple years, and I will be talking about that as well. I think that's actually one of the main intellectual challenges, not just kind of a practical thing. Because they're full of bugs, these things are not such a concern, right? Because, yeah, the bugs are the real concern now, right? But
What's the implementation of the proof systems?
the,
The bugs are the implementation of the, like.
yeah, mostly. Yeah, I mean, bugs fall into many different classes from, I mean, people are still like not even implementing the Fiat-Shamir transformation correctly. And this thing comes up over and over and over again. So there's like, 50% of the bugs are things like that just keep coming up over and over again. But then others are much more subtle. Some would like the constraint systems are just under constraint, you're missing constraints. Others are in the proof systems themselves, all kinds of bugs. So once the bugs are mostly gone, then people will take the training wheels off. And then these things are gonna, so I'm gonna say like in the open problems, like in the next couple years, bugs are the main concern. After a couple years, they probably won't be. And then getting more confidence in security of all this stuff, I think turns to the main concern. Yeah. Okay.
If you are thinking about making money by attacking it, just keep in mind Ethereum can do a hard fork.
Yeah, in blockchain context, there are questions about even if you do an attack, are there ways to mitigate the fallout? It still won't be a happy situation though, ultimately.
Yeah, but people keep coming up with new SNARKs, new proof systems, and then they need to be implemented. So the fact that you didn't have bugs doesn't mean there are plenty of opportunities.
Yeah, so the hope is that things converge a little bit eventually, and also that we develop frameworks, like formal verification frameworks, so that every time something improves, we're not starting from scratch all over again to get all the bugs out. But it's a major, I think, as much as the theoretical cryptography questions, it's an intellectual challenge. These are just way more complicated cryptographic protocols than what are deployed today in widespread use. Question there?
It's worth mentioning that this hacking is 2 times precise saving. It's actually very meaningful for theoretical science, right? Because the hack implies some breakthrough in theory, while the capacity bomb doesn't work.
Yeah, I mean, so these questions, the open questions that these deployments are sort of assuming a happy answer to the open question are very natural coding theoretic questions, right? So if you come up with a better attack, that will be interesting also just from a coding theory perspective. That said, this is very related to whether you can go beyond the Johnson bound for list decoding Reed-Solomon codes, and it's not known to be equivalent to that. So it's still like a question that it's natural in its own right, but it's not, progress on one doesn't imply like a breakthrough in decoding Reed-Solomon codes or something in a black box way. The progress might come via a breakthrough in decoding, yeah. Other questions?
So I was wondering if it's computationally expensive, why is the effort to put it directly on chain? Just not move it out of the chain and do it asynchronously.
Yeah, I mean, people look at things like, posting proofs, on somewhere off chain, and then only posting an aggregation of all those proofs on chain. People look at all these architectures. Yeah. So the extent to which verifier costs matter depends on your application, and can you do things like keep the proofs off chain, stuff like that. Okay, so that's the security stuff. On the performance side, in practice, like logarithmic factors and even constants matter a lot. And in fact, if you don't care about logarithmic factors, we're pretty much done up to all the security questions from the morning. And then simplicity matters a lot, in part because of the bugs issue, right? The more complicated the protocol is, the more likely it is there are bugs, the more surface area you have to deal with if you're trying to get confidence there aren't bugs, stuff like that. Okay, so good. One more point I want to make, which is extremely controversial, and I think most people disagree with me, since this is Simon's Institute for the Theory of Computing. I actually firmly believe that you do not have to implement these SNARKs to have a very good idea of how they will perform. This is very unusual in algorithm design writ large. Typically, if you implement a practical algorithm, It can have wildly, different behaviors on different class of inputs and things. I think in SNARKs, at least for, some SNARKs, which I hope are the right ones, the prover work is nearly data oblivious, not completely, but mostly. And the dominant operations all have a predictable cost, right? So, if you exactly count everything the prover does, and I'm not talking about asymptotics, I mean like, to prove, a RISC-V execution of T cycles, the prover does, 3T of this and 2T plus, 6 root T of that. Like you will know within like a small constant factor how fast the prover is, right? And what that means is everybody in this room can contribute to SNARK design, even if you don't feel like or aren't comfortable implementing the things, right? I can't promise the reviewers will take your paper; they probably won't, but you will know, even without implementing it, if you've made a significant advance or not. Okay, so for the rest of the talk, part one is sort of talking about older work. Older in SNARK land means 5 years ago or prior, and then part two is like the latest trends. Let me just, so 30 minutes in. All right, so yeah, I'm gonna start with polynomial commitment schemes, give kind of a crash course on them. And before I tell you kind of the big picture about polynomial commitment schemes, let me just give a little bit of background on cryptographic groups, because I think the big picture will make a lot of sense if you just understand a little bit about cryptographic groups. All right.
For the performance, I guess there's a lot of things that matter, like how you translate it to the constraint system.
Yeah.
What operations the constraint system support.
Right.
Like, I guess it's not that easy to just look at the scheme and draw the conclusion how fast it is for a specific application.
Right. Yeah. So all of that's right. That there's multiple components to a SNARK, and so if one SNARK supports this class of constraints and another SNARK supports this other class of constraints, it's just you can't really get a direct comparison between them in theory. This is one of the nice things about converging around something called ZKVMs, which I'll talk about in the second half of the talk. It sort of enables much more direct and apples to apples comparisons. These issues come up, like moving to practice doesn't resolve these comparison complications, right? Any comparison is always complicated, whether you're counting operations or seeing how fast it runs on a laptop or a GPU or something, right? It's like, the confounding factors are there in both cases. Yeah, so, but people are converging enough that it's becoming much easier to directly compare different techniques and SNARKs.
Yeah, but I guess oftentimes if your proof that the structure is known, you don't want to use ZKVM. Directly doing it is much faster.
That is highly application dependent, but yeah, I mean, so, my belief is the right proof techniques for ZKVMs will also be the right proof techniques for, specific applications where you're willing to specify a circuit or constraint system by hand. Yeah, but, like I said, my previous slide is highly controversial and most people disagree with me. So we could maybe just leave it at that. But yeah, so I think exactly counting operations is very meaningful, in fact, more meaningful than most implementation comparisons, which are actually deeply flawed on average. Yeah. Okay, so cryptographic groups. Yeah, so, with groups, you can call the group operation addition or multiplication. For a moment, let's call it multiplication. And so a key operation that these commitment schemes do is what's called a multi-exponentiation. Okay, so this means you have a bunch of group elements, say n of them. You raise each one to some power, right? And then you munge all the results together with the group product. Okay. So that's called multi-exponentiation. And if I change the group operation from multiplication to addition, which is just a nomenclature change, now it's what's called a multi-scalar multiplication, right? Each exponentiation becomes what's called a scalar multiplication. Okay, and so with this additive group view, you can think of the MSM as like an inner product. It's kind of a funny one though, because one vector is group elements and one vector is field element or is exponents. Yeah. Okay, questions about this? All right. So many of these commitment schemes, the group elements, this is the common reference string. It's just randomly chosen group elements. Right, and in practice, this would come from evaluating a cryptographic PRG on some seed that everyone agreed upon or whatever. Okay, so Peterson commitments is literally just like if I want to commit to a vector X of field elements, I just treat them as exponents, where the bases of the exponents are from the commitment key. Okay, so Peterson vector commitments, you commit to a vector field elements, it's just MSM. MSM, that's the commitment. All right. So how expensive is an MSM? Well, like the naive algorithm would just take each GI to the XI and compute it independently, and then do the group products, right? And that would be very slow because each, these exponents are like between 0 and 2 to the 256. Okay, so they actually take hundreds of group operations to do just one exponentiation. Okay, so there is a more sophisticated algorithm called Pippinger's algorithm that basically saves a log n factor compared to the naive thing, and it reuses work between the n exponentiations happening. Okay. Good. So, and that log n savings, it's a big deal, right? Because think of n as millions or billions or something, so log n is 20 or 30. I mean, so this is like an order of magnitude savings. All right. Now, the other important point is that if all the exponents are small, you can save another factor of 10, right? So like each of these exponentiations, if the exponents were just like arbitrary field elements, were like 400 group operations, group addition, group multiplications. It goes down to something like 40 with Pippinger's. But then if all your exponents are small rather than arbitrary field elements, it goes all the way down to potentially as little as one group operation. Okay, and this is just like, raising something to, the 2 to the 16, power 2 to the 16 is 10 times faster than raising the power 2 to the 160, right? This you would do by taking GI and squaring it and squaring that 16 times. This you'd have to do 160 squaring. So small exponents are faster to commit to. All right, so this is everything you need to know about multi-exponentiations, like in a slide, and then I'll give you the the big picture of polynomial commitments. Okay, so if you're committing to a 0, you do nothing, right? GI to the 0 is 1, and it just doesn't change the product, literally free. Okay, if you're committing to a 1, that's just one group operation, right? And then it's non-obvious, but if you're committing to something that's small, like 2 or 3 or up to thousands, it's still just about one group operation. Okay, so small values are much faster to commit to than big values. Even though the small values live in a big field, they're fast to commit to. So we call this cost profile for commitments pay per bit commitment cost. It's like the bigger the values you're committing to, the more expensive it is to commit to them. All right, so not all values are created equal. All right, now,
I have a question.
Yeah.
So if you knew the factorization of p minus 1, you could reduce the exponent, and then it would be cheaper for you rather than squaring. And that doesn't mean that you can solve discrete law. I mean, you can, I guess, a little better. So
if you could do what?
it's factor p minus 1.
P minus 1 is known. These are small elliptic.
Oh yeah, I see.
So you could do tricks like that.
Yeah.
But no, I think usually they take G to be of order P. It's not like ZP star. The order of the group is
Yeah, that's right.
prime.
That's right.
So you can't
Yes.
factor it.
That's right.
Right, because you're not in ZP star. Yeah, and if you are, you're in like mine's safe prime.
Okay, so one thing I want to kind of tell you about during this talk is how important it is to only commit to small values. Okay, and the importance of this has actually been established for a couple years already, but I think people are still not quite fully aware or appreciating of this. I'm hoping that this talk helps a bit. So you can look at some of the popular elliptic curve libraries in deployed SNARKs, and some of them are just not optimized to take advantage of small values. It's not hard to do. So yeah, just this is a message I want to be more widely appreciated.
How much freedom do you have in choosing to commit small values?
Well, that's where the polynomial IOP comes in, and yeah, so the latest greatest polynomial IOPs, they ensure you only have to commit to small values.
So the reason you're taking a prime order is because it's supposed to be more secure?
I mean, we want to work over fields for a variety of reasons. The standard elliptic curve groups kind of force you, they have a prime order field, if their scalar field is prime order. People have studied power of prime order elliptic curve groups as well. Some attacks on them are known, but SNARK people have also looked at using them, just making the known attacks fail, right? Anyway, so yeah, I mean, I'd say what's really just going on, the use of elliptic curves limits what fields you can use, but all SNARK machinery today tends to go through finite fields, so we have to use some field.
I don't understand the point you were trying to make with this table. What should I see with these numbers?
Yeah, what you should see is that, okay, so Halo 2 curves is a library that started from the Zcash project and is now run, I think, by Ethereum's privacy and scaling explorations group. Okay, and if you're committing to small values with Halo 2 curves today, it's very slow. It does not have to be that slow. So, here's another commitment scheme implementing the same operations, and it's 10x faster for small values. Okay.
Why is this 32?
Yeah, that's a weird thing about Halo 2 curves. Yeah, it's so Srinath said he ran these benchmarks for me, and I kept asking him about that. Yeah, I don't know. So it's a quirk. Yeah.
So your message is that Halo 2 is
that. Yeah, I know. Okay, before the last couple years, like most SNARKs required the prover to commit to random values. So no one knew to optimize for the case when all the values are small. Now we're getting major speedups by ensuring the prover only has to commit to small values. But if people don't know about it, then you're not going to get the speedup. That's what I'm trying to say.
I have one more question. If the speedup depends on the value, isn't that very much open to a timing attack?
Potentially, yeah. But if you promise that all the values are, if you yeah, so ZK, you might have to worry about that, not security, not soundness. If the PIOP promises that all the values are small, then no. Okay, but yeah, and people, in privacy-focused applications, people should worry more about this. And in fact, techniques where the prover time is highly input dependent. Now, I think generally for the right techniques, the prover time is largely input independent. But people are deploying techniques where it's highly input dependent. And in a privacy-focused application, that has its own problems, timing attacks.
Are the systems today?
Yeah. You could try things like that. I don't think that really. So the N is going to be in like the millions. So I don't. Maybe you could do some of this. Maybe. Yeah, it's worth exploring. No, so generally, generating these GIs is pretty expensive. You have to run something called. You run a PRG, but then you have to call hash to curve, and hash to curve is pretty slow. So you really only want to do this once and then produce many proofs with the same commitment key. Yeah. Other questions? All right, good. So with that, information about curves out there, I can give a high-level overview of polynomial commitment schemes, and sort of here it is. So we can get a bunch of good properties out of curve-based commitments. I sort of already covered zeros are free to commit to and small values are fast to commit to. We can also get the verifier cost to be logarithmic. Sort of this was known for a long time. If with KZG commitments, that's even constant verifier cost. But now it's known you can do it with other techniques as well. They can be transparent. Okay. The polynomial evaluation proofs can be very fast to compute. So not much more time than just computing the requested evaluation. And the commitment key can be sublinear in size. So you can commit to like degree n polynomials with a square root n size commitment key. That lets you commit to bigger polynomials. Okay.
Wait,
yeah.
So far you just talked about Pedersen commitment, but you need to actually do a polynomial commitment.
Yeah, I haven't told you how evaluation proofs work. Yeah, I've just told you how to commit. Yeah. Okay, so these are a lot of nice properties. And actually, I'd say that these bottom two properties are a little bit underappreciated. They're very powerful. And I do want to give you a sense of how evaluation proofs might be what they are. So I was, if I have time, it looks like I'll run really quickly through one example. Okay, and this example also will show how you can get these two properties. Now, these lattice-based commitment schemes that are still under development, I basically think we should be able to get all 6 of these properties, okay? But whether or not, we haven't done it yet, basically. And if we can do it with lattices, we'll get post-quantum security, and we'll also, these elliptic curves, they force you to work over certain kinds of fields. The lattices don't necessarily force you to work over those fields. So you can hope for significant concrete speedups from switching from curves to lattices and thereby working over different fields, okay?
We have like hash-based polynomial commitment?
We do. Okay, and I will say a little bit about them, but the main thing so hash base you can also work over, lots of kinds of fields. You do need to typically encode with an error correcting code, and the code that tends to lead to the smallest proofs is Reed-Solomon. And so if you want fast encoding for Reed-Solomon codes, that actually does restrict a little bit what field you work over.
No, but wait, you can't just, you're thinking of like Merkle hashing Reed-Solomon.
Yeah.
Okay, but then the field is very small.
No, your field is big. The Reed-Solomon code word is just evaluating a small subset of the field.
But what if you want to open
there are ways to deal with that. Yeah. So I'm not going to talk too much about hashing-based commitments today. So these are actually the most popular commitments, and a big reason they're the most popular right now is because they let you work over whatever field you want, subject to the need for FFTs or whatever if you're using Reed-Solomon codes and stuff. But my view is that there are underappreciated benefits of these other classes of commitment schemes that actually outweigh that field flexibility choice from hashing. And in fact, lattices can give us more or less the same flexibility, if not better, while still having the other properties that are so nice from the other schemes. In particular, hashing schemes cannot give you, or we don't know how, free zeros. Okay, and I'll just tell you now why, so I don't have to say it later. With hashing-based schemes, the very first thing you're going to do is like take the coefficients of your polynomial and encode it with an error-correcting code. Typically, it's a linear error-correcting code, and if that code has good distance, then by definition, like a single non-zero entry in the message turns into a constant fraction of non-zero entries in the code word. And so, you don't get free zeros, basically, right? You could have all zeros but 1, 1, and you still have to pay like linear time in the whole message size, more or less.
Do we know the bullet 6 without bilinear math?
No. Well, sorry, not with constant size commitments. So if you let the commitment be annoyingly big, then we can do it. In fact, I'm going to show you that right now. If you want the commitment to be constant size, you need bilinear maps. Yeah.
Wait, sorry. So sublinear commitment key, sublinear in the polynomial you're trying to commit to?
Yeah. So, right. So for hashing-based schemes, the commitment key is like nothing. It's just, here's the hash function, right? For these other categories, the commitment key is actually big. It's like a whole bunch of group elements or something. Okay. So the commitment key can be a limitation, right? But in return for that limitation, you get free commitments to zeros. And by the end of this talk, you'll see why that can be powerful. Okay, other questions? All right, so yeah, let me just quickly cover one commitment scheme just so you can see what an evaluation proof might look like, but also so you can see how you might achieve these two properties, okay? So this is called Hyrax, although it was based on an earlier paper of Boodle and others. So the big downside here, which is exactly what we were getting at with your question, is that the commitment size and the proof size is square roots, not constant or log, okay? But on the plus side, the commitment key size is square roots, not linear, okay? It's transparent, and the prover is very fast, okay? And in particular, the evaluation proofs, I call it an opening proof here, the evaluation proof, you really don't do more work than just evaluating the polynomial at the requested point. There's a little more work, but it's not really relevant. Okay, so here's the structure in polynomial evaluations that this scheme exploits. I call it vector matrix vector structure in polynomial evaluation queries. This scheme directly applies to both univariate and multilinear polynomials. Let's focus on the univariate case. So let's say that, here are the coefficients of the polynomial we want to commit. This is C0 up to Cn. What we're going to do is, well, the evaluation of P at the requested point is just an inner product of the coefficient vector with the vector of powers of the evaluation point, okay? Now, this second vector, powers of 1 point, it has a lot of structure to it. It's not some arbitrary vector, and that's what we're going to exploit. So in particular, so I can take the coefficients and write them out as like a root n by root n matrix, and now this inner product is a vector matrix vector product, right? The matrix depends only on the polynomial. The two vectors depend on the evaluation point. Yeah, that should be R. Sorry, I meant to change. Yeah, thank you. That should be R cubed and R to the sixth, not R squared and R to the fourth. Yeah. These are powers of R to the root n minus 1 or plus 1. Yeah, anyway. Thank you. Okay. All right, great. So the commitment to this polynomial is I just do a Peterson vector commitment to each column of the matrix. That's it, okay? And that's, so it's root n MSMs, each of size root n, and that's more or less the same cost as one MSM of length n. The Pippinger speed up falls a little, but yeah. And this is, so the commitment is pretty big, but it is sublinear. All right. And now for the evaluation proof, and I'm going to use additive group notation here, right? The verifier says, hey, tell me this vector matrix vector product, where the verifier knows these two vectors, okay? And basically what all the prover is going to do is it's just going to compute one product on its own, m times a. That's the proof, okay? And the verifier is going to, on its own, compute a commitment to m times a and make sure that whatever the prover sends indeed opens that commitment. Right? If the verifier is a commitment to m times a and the prover sends it something that opens the commitment, the prover has really sent it m times a. And once the verifier knows m times a on its own, it can then take the inner product of that with b. That's it. That's the whole thing. So how does the verifier get the commitment to m times a? Well, it's just homomorphism, right? So if I want, the prover has sent a commitment to each column, right? Now, if I multiply the matrix by a, right, that's just like an inner product of the columns with a, and yeah, it's just homomorphism, right? You can get like a commitment to a sum by taking a sum of the commitments. That's it. So that's Hyrax, right? That's the evaluation proof, right? And it's not very popular as a scheme because of the high verifier cost. Commitment's kind of big, proofs are kind of big, but they are sublinear. And you can see the commitment key is small because you kind of, commit to things in pieces, one column at a time, right? And the prover has to compute m times a just to evaluate the polynomial anyway, really. Like that's the fastest algorithm, more or less, to do the evaluation. So, all right, hopefully that's a little bit helpful. Okay, so, I've told you both the good things and the bad things about Hyrax. Let me give like a whirlwind tour of how to address the bad things. So, what bulletproofs gets the commitment size down from root n to 1. So that's good. And it makes the proof, the evaluation proofs logarithmic in size rather than root n. So all that's good. The bad things are the commitment key goes from root n to linear, and the verifier and prover both get really slow. Okay. Dory kind of achieves the best of Hyrax and bulletproofs. And I'll just tell you like the key idea. Is you take the Hyrax commitment, that's size root n, we're not happy. So you commit to that you commit to the Hyrax commitment.
What's the prover time for the first one again?
For bulletproofs?
Hyrax.
Hyrax, it basically just evaluates the polynomial, right? So it does m times a. It computes, so this is the coefficient matrix. Just, the coefficients of the polynomial arranged as a matrix. And a is like the first root n powers of R. And so, it's like linear field work, but more than that, like the way the prover would naturally go about evaluating the polynomial is to compute the powers of R, right? And then, start taking the, it needs to, this is the answer. It's just, computing the answer. It's kind of like a partial version of the full answer. The full answer is bt times m times a, and it's computing m times a. So there's no cryptography in the in the computing the evaluation proof. It's just here's the m times a. Okay, so yeah, so this is the key idea for Dory, which is a paper by Jonathan Lee from several years ago, right? And basically, you take Hyrax, it's got a lot of nice properties, but the commitment's big. So don't make that commitment final, commit to the commitment. We still want nice things like homomorphism. And so, preserving homomorphism while letting you commit to a commitment is a little bit, you need to be clever, but you can do it. All right, questions? Okay, so I think I said most of what I wanted to say about hashing-based schemes, right? I really, they let you, the commitment in hashing-based schemes is like you encode the coefficients of the polynomial with an error-correcting code, and then the commitment is just a Merkle hash. Okay, that's, you know, at high level, that's how all the hashing-based commitments work. And then the, okay, so opening, I really just want to sketch this, but basically the verifier starts requesting certain random linear combinations of the committed vectors entries. Okay, so like to give Fry as an example, right? The commitment is like, you know, you read Solomon encoded the polynomial that you want to commit to, the commitment is the Merkle hash, and the opening proof is roughly this is what happens inside of it. You cut the committed vector in half, and you randomly combine the two halves, right? And the prover commits to that, which is now half the size of what you started with, and then you just do that again and again and again. You know, that's the opening proof, and then you do some consistency checks. So the opening proof is like the commitments to these, we call them like kind of folded vectors, and some consistency checks. Yeah, and you can sort of, well, I'll just leave it, you know, I don't want to spend all my time on the commitment schemes, but yeah. Because you lack homomorphism, you know, you have to do a lot of consistency checks, and that's why these proofs get up to, you know, 100 kilobytes and more, and yeah. Okay, I guess one thing I will mention, because it's been some important progress recently, is so hashing-based commitments cannot give you free commitments to zeros, but they can give you pretty fast commitments to small values. Okay, and I want to mention how you do that, how you can do that. Okay, so all of these hashing-based schemes, to get adequate security, they ultimately have to work over like a 128-bit field, generally a lambda bit field somewhere, right? So you need a big field somewhere in the scheme. Okay, so if I want to commit to a bunch of small values, so let's just say like a bunch of zeros and ones, the naive thing to do is just assign one field element to each value, right? And now just commit to all those field elements. Okay, so these new works, especially Binney has started this, and now there's Blaze, is what they'll do is they will take a whole bunch of those small values and pack them into a single field element, and then commit to the packed things. Okay, and so, you know, if you're committing just to bit vector, this will let you commit to like 128 fewer field elements, right, than if you didn't do the packing. Okay, that's the main idea. Now, you know, we're not done, right, because, you know, the verifier really cares about the unpacked field elements. So in the evaluation proofs, or really you can phrase it as in a PIOP language, but anyway, you need to have a way to relate an evaluation of the polynomial you obtain from the packed things to the polynomial you would have obtained if you never did the packing. And that's where the real cleverness lies. Okay, so hashing-based schemes, you can get pretty fast commitments to small values, but you cannot get free commitments to zeros.
Which one is the best if I want to optimize the prover time?
I mean, so my personal view is that the curves and lattices have benefits that outweigh the benefits of the hashing schemes. I am one of the few people with this view, so it's a very complicated question.
Is it possible for you to compute the proof with, let's say, you know the evaluation outcome, and can you compute the proof without having to read the whole polynomial? Is that possible?
There actually is some work on this, but it kind of falls right out of an algorithm for, or data structure for polynomial evaluation due to Umans, and I'm sorry, I don't know the other author. But it assumes that the committer is honest, which comes up in some settings, but not the main ones. So I'd say this might be an open question. Yeah, I'll leave it at that.
You're talking about the polynomial data structure. You can, that allows you to evaluate the polynomial in, let's say, polylog time.
Right.
But I'm just saying, like.
But if your commitment is just a Merkle hash to that data structure, then your evaluation proof is just let me run, you know, the polylog time algorithm, and anytime it queries the data structure, I give an authentication path. Anyway, so
that only works for small fields.
Yeah, that's true. Yeah, and it's also impractical. So as far as practical SNARKs go, it's a hotly debated question: curves versus hashing versus lattices. You know, hashing has a lot of flexibility in field choice. It doesn't give you free commitments to zeros. You know, these things work against each other, and what comes out ahead is a very complicated question.
why are zeros so important? Like,
You'll see in the second half of the talk. Yeah. Historically, they haven't been. Like fast commitments to zeros has not been something people have really exploited much until very, very recently. So, yeah.
Because all of the polynomials that are being committed, aren't they all, like in zero knowledge proofs, aren't they just masked by the IOPs? Or
Aren't they?
Random field elements?
Aren't they masked?
Oh, masked. So you often don't need much masking. So you might have, gigabytes of real data that get masked by a tiny, tiny amount of random things. Also, in many applications today, people just don't need to care about the ZK on top of that. So, yeah.
For the question of hashing versus curves, small field makes sense if you are talking about current hardware, but if you are allowed to design custom hardware, is there a outright choice that elliptic curve or lattice-based techniques?
I would say, so the situation is, again, the trade-offs are like very complicated, right? And there's no easy answers. If you want very fast commitments to small values with hashing-based schemes, seems you want to work over binary fields, right? Because they can let you pack like 128 bits into a single field element, right? GPUs today, they don't have good support for binary fields. So if you, and GPUs tend to be like cheapest per unit of compute in the cloud, right? So if you really want to use GPUs, you don't want to go the binary field route, right? The binary fields have other complications, but in other ways, they're very nice, right? So for FPGAs and ASICs, people are very bullish on binary fields. They're definitely not on GPUs unless they kind of get added to, GPUs like NVIDIA add to them. You can speed up any of these things with specialized hardware. We can talk about this for hours. Yeah. Okay. Okay. So, yeah, let me just skip over the lattice stuff. Like what I would really want is for lattice schemes to just directly replace the curve schemes, right? So I want all 6 properties. And the summary of the lattice schemes is like we have some of these properties, but certainly not all of them at once. I guess what I can say is we have, if you just focus on the commitment phase, we actually already have lattice-based commitment schemes that have super great commitments with, zeros are free to commit to, small values are fast to commit to, and all this stuff. But that scheme doesn't yet come with like a really nice evaluation proof. And so there seems to be a lot of work left to do, and I'd love to inspire more people to look at that.
And what's the main motivation? Is the post-quantum or?
So 2 things. So post-quantum is a major motivation, and the other thing is, the curve stuff you have to work over a 256-bit field. With the lattice stuff, you can work over a different field, and potentially get like almost an order of magnitude prover speed up just from switching the field.
Wait, no, but like hash-based is also post-quantum, and also you can work on any field. So
Yes.
what's the advantage of lattice over the
hashing?
The hashing.
The main thing is free commitments to zeros.
Yeah.
Yes. And we only knew how powerful that was based on very recent work, right? And yeah.
I think also two-sided.
Yeah, that too.
Assumptions it's much smaller.
Yeah. Yeah, so we can unpack the many layers. If you want to do recursion, it's much nicer to prove you're doing these, like algebraic operations than non-algebraic hashes. We also have algebraic hashes. There's like 50 different things to consider, but yeah, the main thing though is on the prover side, right, is the free commitments to zeros. Yeah. Okay. Let's see. How late did I start?
I think might be a good time to stop.
Can I take 3 more minutes? Okay, 3 more minutes and then we'll take a break. Okay. All right, so that's polynomial commitment schemes. I'd like to start talking about polynomial IOPs. And I will go through the univariate polynomial IOPs now, and then everything after the break will be sum check. Okay. All right, so yeah, I want to just give a clear sense of how the univariate polynomial IOPs work, and so I want to focus on one particular problem, which is at the core of a lot of SNARKs, that use univariate polynomials, which is the prover has committed to 3 polynomials, A, B, and Z. These are univariates, and there's some set of size n, Often it's the nth roots of unity, but don't worry about it. It's just some set of size n. And the claim is that for every input in that set, this is a subset of the field. So for every field element in the set, if you evaluate A at that point, multiply it by B at that point, it equals C at that point. Okay. Now this, typically what's going on in the SNARK is like A is capturing the left input to gate I, B is capturing the right input to gate I, and C is capturing the purported value of gate I, and gate I is a multiplication gate. And so this is checking, is the value of gate I really the product of its two inputs? Okay. Now, yeah, so let's consider what we call the vanishing polynomial of the set H. This is just the polynomial that maps everything in the set to 0 and nothing else to 0. So if the set is the nth roots of unity, if you're working in a field that has nth roots of unity, this vanishing polynomial is just, x to the n minus 1, right? Because this exactly kills the nth roots of unity. Okay, so there's a simple fact, easy to see, which is that the prover's original claim is true if and only if, this polynomial g, which is a times b minus c, is divisible by the vanishing polynomial. Okay, so one direction is like completely trivial, right? It's like, if I can write g as some quotient times the vanishing thing, then obviously, this vanishes at anything in H by definition of the vanishing thing. And the converse is, holds as well, kind of pulling out all the roots of G or something like that. Okay, so how does, quotienting work, this, univariate PIOP? So, the prover just commits to the quotient. That's it, sends the quotient. And, the verifier now needs to check, does G really equal Q times the vanishing thing? And all the verifier is going to do is sample a random point and confirm that that equality holds at the point. Right? Obviously, if the equality holds, at all points, it holds at a random point. And, two low-degree polynomials that are not the same, G and the right-hand side, they, only if the prover gets really lucky with the choice of R will they agree at R. Okay, and so that's it. That's quotienting. And, so the verifier needs to evaluate each of these polynomials at R. A, B, C, and Q were committed, so the polynomial commitment scheme comes with a way for the prover to give the evaluations. And then the verifier can evaluate the vanishing polynomial on its own very quickly. If this is like x to the n minus 1, you just, with log n squarings, you get r to the n and subtract 1, and that's it. Okay, so, why is this, by the way, this is great for the verifier if you're using like KZG commitments, right? Because we have 4 commitments. They're each one group element. Okay, and then the evaluation proofs are also just one group element. And in fact, it turns out you can batch them and really just have one evaluation proof for all 4. So now our proof is only 5 group elements or something. It's pretty good, right? For the verifier. Okay, why is this a little bit slow for the prover? So the prover has to compute this quotient polynomial, which means you're dividing like a degree 2n polynomial by degree n polynomial. That already can be kind of slow. And then it commits to the quotient polynomial. Okay, now, important point is we have almost no control over the quotient polynomial. We know what its degree is, but that's about it. And in particular, if A, B, and C only involve, if they were sparse, so they're mostly 0, they only involve small values or something, Q is not going to be sparse. Q is not going to only involve small values. Okay, so that means Q is pretty slow to commit to. All right, I mean, it could be like an order of magnitude slower to commit to than something that only had small values, and then the sparsity thing could be, it depends how sparse, could be an even bigger deal. Okay, so the second half of the talk, you're going to see basically how to avoid quotient polynomials and thereby avoid these issues, and that's why committing to zeros for free and committing to small values quickly is so important, and why I spent most of my first hour on the commitment schemes to explain how the commitment scheme can support that. So I'll see you after the break.